Without graphing. So no graphing calculators on that one. I want you to find me what the shape of that graph will be. I want you to find me the center, and then I want you to eliminate the parameter on it. Okay? Go for it. So without graphing, what shape is this? Why is it an ellipse? Cosine and sine makes it circular in shape, right? Okay, but why is it an ellipse and not a circle? What's not equal? The r value, right? The radius value. Okay. So which way is this? Because an ellipse is a stretched out circle. It's either stretched out horizontally or it's stretched out vertically. Which way is this stretched out? Why horizontally? Did you say cosine has a big coefficient? Okay, because up here it sounds like you just said sine. Okay, yeah. So the cosine, you gotta talk loud because we're like 800 feet away. Okay. So the bigger coefficient is on the cosine. Okay, or the bigger one's on the x. So this is an ellipse. Okay. Where's the center of said ellipse? 2, -4. Did you get unconfused? Whoever just said they were confused?
I said, oh, I'm still doing this.
Oh, okay. Gotcha.
Like I stopped in the middle.
Gotcha. Okay. Now, if this were back in first semester, when we were doing conic sections and we were talking about ellipsi, okay, we would have said that an ellipse with a center at 2, -4 stretched out horizontally a little bit longer, so a major axis on the horizontal, we would have said that this would have had an x - 2 quantity squared over 9 plus y plus 4 quantity squared over 4, and then that equals 1. That's what we would have said first semester if we had just gotten done with our conic section unit. Okay? So when we eliminate the parameter, that's what we should get. Okay? So because there's sines and cosines in my x's and my y's, when I go to eliminate the parameter, I need to take x equals 3 cosine of t plus 2 and y equals 2 sine of t minus 4, and I have to solve those for what? I need to solve each of those, for the left one for cosine, the right one for sine. So I'm going to subtract 2 first. Then I'm going to divide by 3. And that gives me cosine of t. Over here, I'm going to add 4. Then I'm going to divide by 2. That allows me to use the hammer which gets me, when I square a fraction, I square the top, I square the bottom. When I square a fraction, I square the top, I square the bottom. And so I've eliminated the parameter and got the same thing that we would have gotten first semester. Okay. Love it. Good times. Okay, we're skipping that one. So we're going to go right to this Ferris wheel problem. Okay, so we are going to be riding a Ferris wheel with a radius of 60 feet, a period of 12 seconds. The bottom of the Ferris wheel is 8 feet off the ground, and it's rotating in a clockwise direction. We're starting at the bottom. I want you to find me the parametric equation that goes along with that scenario. Then, when it's all, so after you do that, then what I want you to do is I want you to find the location of the gondola, that's the car you're riding in, when t is equal to 5, and how far that you've traveled if you're riding around and the carny forgets to shut the ride off for 5 minutes, or for a minute, excuse me, 5 minutes later on. Okay? Right? Make it so. Answer me those 3 questions. So, I'm sensing that we're a little stuck. Okay? There's one part that we shouldn't be stuck on, though. What's that part? But what part of the equation should we not be stuck on? Even before that. Because some of us got stuck on that. So what's the radius? 60 is the radius, right? Okay, so that means these are both going to start with 60 because that's the radius of my Ferris wheel. Okay, now x is, y is, okay, so that should be the next part. So then this is cosine, and this is sine. With me? Okay. Now, we need to know direction of spin. Right? Clockwise. So is that a positive or is that a negative direction of spin? That's negative because it's opposite the unit circle. Okay? So that means that this B here is going to be negative because of the clockwise spin. With me? Okay. What's my B value? My period value. How did you come up with that? Oops, I should do it this way. My B value is 2 pi divided by my period, and my period was 12 seconds. So that's going to be pi over 6. Right? Now what comes next in both of them? T comes next. Are we starting on the right side? Because that's 0 on my unit circle, right? Is the right side? Are we starting on the right side? No. Where are we starting? At the bottom. So how do I get from the right side of the unit circle to the bottom of the unit circle? I could go minus pi over 2 or plus 3 pi over 2. Okay? So I could go minus pi over 2 here, or I could go plus 3 pi over 2 there. Anything else that we got to add? We got what? So just plus 8? Why not? Plus 68, because it's 8 feet off the ground, and then there's a whole nother 60 before we get to the center. So really I got to add here on the y part, I got to add 68. Okay? So that's the two equations. Now, type those into your calculator. Actually, before we type that in, we should find our t values. Right? Okay? Where are we going to start putting t's in? What number are we going to start with putting t's in? Start of the ride is when? Start of the ride is when? Start of the ride is when? How many seconds is it? Are we been riding at the start of the ride? 0. Okay. When am I going to end my t's? 12 seconds, because that gets me a complete loop. Right? Okay. What if I went 14 seconds? Is that okay? Okay. So I could go any number there. That second number could be any number bigger than 12, right? What if I go smaller than 12? It's not going to be a full rotation. Okay, so I'm not going to make a complete loop. So now we can type that into our calculator. So we said it was 60 times the cosine of negative pi over 6 times t minus pi over 2. And then we said it was 60 times the sine of the exact same insides. And then plus 68. But we said we had to go with a t value here of something at least 12. You can substitute in where I wrote pi, because I was typing it in on my keyboard, you can substitute the symbol in for pi. Everybody know where to find pi on the calculator? It's on this key down here that's got pi on it. Okay. With me? Hit enter, you should see it, right? Oh. What's wrong? Gotta adjust our window, right? Okay. So, window, let's talk window here. Window settings here. Let's go, what do you think? X's, Y's. 70s in both directions, so negative 70 to positive 70. By 10s. Okay. Y's. What? Need to get at least to what? 130, because we got to maybe 140. Okay. And bottom? 0. I like to see my axes down there though, so I'm going to go with negative 10 to 140. Again, by tens. Okay? Now, Napper and I were up here talking, and every time that he graphs this, he gets this. And that doesn't look like a Ferris wheel. Right? Okay? Because it's not circular. Okay? And the reason is because of the scaling that we chose, okay, it's stretched out horizontally. Okay? And so if you want, it's still in your brain, your brain's telling you it looks like an ellipse, but mathematically wise, it's a circle. It's just the visualization of it. But if you need to actually see that, you can go Window, Zoom, and you scroll all the way down here, and you can square up your window. If you square up your window, and then you grab onto your axes, and you pull it back a little bit, and then shabam, there you go. Now you've got yourself a nice, beautiful, wonderful circle that is your Ferris wheel. Okay? So if you square up your window, it'll do that. Okay? So now we can answer the question, where are we 5 seconds into the ride? And I'm going to do that using the trace. I'm going to set my trace step to 1. And then I'm going to trace it. And I'm going to trace it until I get to t equals 5. So I'm going to start at 0, which is right. We started at 0. 0 better be at the bottom of our ride. It's at the bottom of our ride. Okay? With me? Pull this back a little bit. Won't let me. I'm trying to pull it back a little bit. Pull it back, pull it back. Oh, because I'm escape there. There, now I like it. Menu, trace step, trace. Okay, so we're at the bottom. Yes. Love it. Okay? 5 seconds in. 1, 2, 3, 4, and 5 seconds in. There we are. We are 30 feet to the left of center, and we are 120 feet up in the air. Then it said, find me the position of the gondola 47 seconds into the ride. Okay? So you've got 2 options here. Option number 1 says that you can trace all the way around to 47 seconds. You can do that one of 2 ways. I could continue around 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. Go all the way around until I get to 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47. So there I am at 47 seconds, which is t equals 11. Okay? The other way that you could have done this is I can go back here into this, and I can go here to 47 seconds, and now when I trace, it and I'm at the same spot. which tells me that at 47 seconds, I am 30 feet to the right and 16 feet up.
Riveting internets right now, watching me redo all of this.
Okay. So we got that. Now, the other question that we had was, how far have we traveled if we were on the ride for 1 minute? How many complete laps have we done in 1 minute? How many? 5. Because it takes us 12 seconds to go around one time. So we've made 5 revolutions in 1 minute. What part of the circle are we going around? What do we call the perimeter of the circle? Circumference. So we're traveling along the edge of the circle, which is the circumference. So we've gone 5 circumferences, right? What is the formula for the circumference of a circle? 2 pi r. So this is 2 times pi times the radius. What's the radius? 60. 5 times 2 times pi times 60 is 600 pi. I was off by 2. Tap the brakes. 600 pi, right? Which is 18, what did you say? 84.96 feet. So we've almost gone 2/5 of a mile. Okay? Love it. So I just added those in then for everybody else for when we copy down the notes. Okay? So, motion in a plane. Okay? So it can be shown using calculus that if an object is thrown or launched vertically, okay? So if I'm launching something vertically, so for instance, I have a softball in my hand, I'm going to launch it vertically. So it's going to go straight up, and it's going to come straight back down. Okay? Straight up, straight back down, and if I pull my hand away, it's going to go all the way, it's going to keep going straight down in that motion. Okay? It's going to go up, gravity is going to take a hold, it's going to slow down, it's going to reach its maximum point, it's going to start falling right back down in the same path it came. Okay? And if I'm standing up, if I'm standing at the ground, it's just going to come back and it's going to hit the ground. If I'm standing up in a building or up on top of a building, it's going to go up, it's going to come back down past where I launched it, and it's going to keep going down until it hits the ground. Okay? With me? Okay? So, we can model that, the height of that object, using this formula. And this formula has in it 3 distinct parts. The first part here this negative 16t squared, that is the gravitational constant. Okay? That's gravity working against my object on its way up, working with my object on its way down. Okay? The second part here is my initial velocity part. When I launch something vertically, okay, I've got to put some oomph into it. Okay? The more oomph I put into it, the higher it's going to go. Okay? If I don't put any oomph into it, it's going to stay right there. Okay? So I got to put something behind it. I got to put some initial velocity behind it. Okay? And then the third component is h sub 0, which is my initial height. So I've got those three components anytime that I vertically launch an object. Okay? So let's do that. Let's vertically launch a ball. We're going to stand at the top of Wausau West at its highest point. It's about 30 feet in the air. Actually, a little bit more than that, but we'll say it's 30 feet in the air. Okay? And I am going to throw this ball straight up. And I'm going to launch it with a velocity of 50 feet per second. Okay? Boom, throwing it straight up. Okay? So what's going to happen to the ball? It's going to come up. Remember, I'm standing up here on a 30-foot building. So it's going to go straight up. And then what? Gravity's going to take a hold, and then it's going to come straight back down. We're assuming that there's no wind and there's no other factors going on, and then it's going to go splat and it's going to hit the ground, right? Okay, right? So the function that I can make s of t here, actually we'll say s of x. Let's go s of x, because then when we put it in the calculator here momentarily, it'll be all nice and pretty for us. Okay? So that's going to be negative 16x squared, because that's my gravitational constant, right? Okay? Plus v sub 0, my initial velocity. What's my initial velocity? 50 times t, but in this case we're going to go x, because you'll see why we'll do it x here in a minute. Yeah? Okay? Plus my initial height. What's my initial height? 30. Okay? So what I would like you to do now is, I would like you to put that, start a new page on your calculator. Control doc gets me a new page, a new graph, and since it's a function, that's the function that I want us to graph right now. So it's negative 16x squared. Oops, that didn't work out so well for me. There's the squared. Now I can see it. Negative 15x squared plus 50x plus 30. Even though that those would have normally been t's, we originally made them as x's because we knew we were going to come into this one and I get this. Yeah? Okay? So let's adjust our window to fit that one.
window settings,
X's. Do I need negative X's? Why not? Do I need negative X's? Why not?
The ground and then 0.
No. What is X? We're starting at time 0. Negative X's mean back in time. Okay? Now, unless you're Marty McFly and you got a spare flux capacitor on this roof with you, you don't need no stinking negative X's. Okay? All right? Maximum, still 10. You can keep it at 10.
okay? I'm going to go by ones this time.
Okay? Y's, minimum. Don't need to be negative, right? Because that's the ground, correct? Okay, so I'm going to go negative 5 there, because again, I like to see my horizontal axes. How high do you think that ball is going to go? 75? Okay.
I'm going to go by fives then.
Good guess. 75. Okay. Now, that does not look like the path that our ball took. Remember, we said that our ball was going to go straight up and then come straight back down. This does not look like that, correct? But I can analyze this graph, correct? What can I analyze it for? I can find its maximum. Menu, come on, menu. Oops, wait, tap the brakes. I see now what's going on. I gotta put this thing down here. Menu, analyze graph, maximum, gets me a maximum height of 69.1 feet. Yes? What else can I analyze this graph for? Well, the maximum height, 1.56 seconds. What else can I analyze this graph for?
How long the ball is in the air?
What do I do with that one?
You can, like, where the 0 is.
Yep, find the 0. Analyze, find me a 0. So it hits 0 at 3.64 seconds. Right? Okay. So and you've done all this stuff before. You did that a lot in algebra 2, okay? Some in geometry, a little bit in this class so far. Okay, we're finding zeros and all that stuff. We did some of that first semester. Okay, so you got that. Now, what I want you to do is I want us to give the true flight of that ball. Okay? First off, okay? So we can make a parametric equation of this, and we can determine what it is based off of that information. Now, when I throw the ball vertically, okay, so I'm going to throw this ball up vertically. What is the horizontal, because X is horizontal, remember. What is the horizontal movement of it? What do you mean? It's not moving horizontally at all, right? Okay. So the horizontal component for my parametric can be any number that you want. Okay? Because it's not going to be a factor. All you're doing with the X part with a vertical motion problem is setting where it is on your graph. Okay? So I'm going to set mine at 5. But again, this could be here any number you want. because there's no horizontal movement, you can set it to be anything. I would not choose 0 though, okay? Because then it's going to be right on your axes and it's going to be hard to see. Okay? But it can be any number that you want. Okay? Okay? My y of t is going to be negative 16t squared. In this case, I had an initial velocity of 50, and I had an initial height of 30. That's my function. Now we're on with t's. Okay? And then I need to set my t values. What t values should I go with? When do we start calculating the height? At 0, right? When I initially launch it. So we're going to start at 0. When does it hit the ground? 3.64 seconds, right? So let's go to 3.64 seconds. And let's go with a t-step here of 0.13. Okay? Make yourself a brand new page and graph that for me. So I get that as my motion. But what's wrong with that? Kind of rounded it at the bottom, never hit the ground, right? Okay. So to make it hit the ground, oops, let me get back onto this. I'm going to go with my t-step here. Actually, I'm going to go to 0.7. And now it hits the ground. It's that whole rounding thing. Okay? Alright? I added a little bit to my t values. Instead of 3.64, I went 3.7. And now that's true motion of that ball. Going straight up, coming straight back down, which we can show when we trace it. If I go here and I menu trace this, trace step, I'm going to go a t-step here of 0.5 seconds because it's only in the air for 3.5 seconds. Okay, so there's the ball at my start. I'm 30 feet up in the air. And then it goes up, 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 down, 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 and then it goes back to 3.7. Here it is, so it's a little bit low. So I was a little bit low by 4 feet. So I could adjust that number to get it closer and closer to 0. Okay? With me? Now, how many times do you throw something straight up in the air? Very few, right? Okay? Alright? So, to adjust this so that if we're not throwing it straight up, so let's say now I'm standing on the top of West, and I throw the ball out at an angle, okay? Or I'm standing on, since I'm looking at the picture of Lambeau Field in the back there, if I'm standing at the top of Lambeau Field and I throw a football, okay, to somebody, or I'm throwing that at an angle, okay? I'm not throwing it straight up, I'm throwing it at an angle, okay? So we're going to assume that gravity is the only force acting on the ball. Okay. Same scenario, but now instead of it throwing it vertically, I'm going to throw it straight out we need to assume here that we've got a velocity vector going on, right? Because when I throw that, I'm throwing it on a vector line, okay? But now my angle that I'm throwing it at, or the vector I should say, would be the magnitude or the initial speed, that's the magnitude, the initial velocity, if you will, times the cosine of whatever angle I'm throwing it at, and then the magnitude times the sine of whatever angle I'm throwing it at. Okay? So I got to add in that vector into my two parts. Well, here's how those get added in to make it so that our path looks like that. Okay? So now our x part of our parametric equation needs to bring this in. So that's going to be v sub 0 times the cosine of the angle that I'm throwing it at. And all of that is going to be times t. T is not part of the cosine. T is part of, or the v sub 0 cosine of theta is part of the coefficient. And my vertical component is going to be negative 16t squared. I still have my gravitational constant, plus my initial velocity now is dependent upon my angle, my vector that I'm throwing it at, times t, plus h sub 0. And from that, then, now we'll be able to figure out maximum height of the ball if I throw it. If I'm standing on top of West, I throw it at a 65-degree angle in the snow. It's snowing again. Let me show you. See how high the ball gets? I can see how far the ball goes. I can see how long the ball is in the air from all of that. Okay? And that's where we'll pick